Welcome to the second lecture of Advanced and Miscellaneous Metrology. In this lecture, first of all, we will see about the basics of the optical interference and interferometry. Now, the phenomenon of interaction of light waves is known as interference, and the instruments designed to measure the interference is known as interferometer. We will study the various instruments that is working on the concept of the interference, that is nothing but mixing of light waves. The first device that we are going to study is optical flat. Now, optical flat is a circular piece of optical glass or fused quartz having its two plane faces flat and parallel, and the surfaces are polished to an optical degree of flatness. Optical flats made of quartz are more commonly used because of its hardness, low coefficient of expansion, resistance to corrosion, and much longer useful life. So most of time optical flats are made of quartz. The optical flats can be of two types. The first one is type A. It has only one flat surface and it is used for testing flatness of precision measuring surfaces of the flats, slip gauge and measuring tables. The second one is type B. It has both surfaces flat and parallel to each other. They are used for testing the measuring surface of the micrometers, measuring anvils and similar length of measuring devices for testing flatness and parallelism. So we can say that type A has only one flat surface and type B is having two flat surfaces. Okay. Now let us check the figure of the optical flat to understand its construction and working. This is the figure of an optical flat. When an optical flat is placed on workpiece surface, it will not form an intimate contact, but it will be at slight inclination to the surface, forming air wedge between the surface as shown in the figure. Here we can see it is the air gap, or it is also known as air wedge. It is due to inclination. The optical flat is now illuminated by monochromatic source of light. Interference fringes will be observed. That we will understand later how the fringes is generated. These are produced by the interference of light rays reflected from the bottom face of the optical flat. This is the bottom face of the optical flat, and top face of the workpiece. This is the top face of the workpiece. So there is some difference between the light rays reflected from the bottom of the optical flat and top of the workpiece, and this is how the fringes is generated. Now let us understand this by an example. When a beam AB of monochromatic lights fall on the optical flat, this is the beam AB and it is falling on the optical flat. It travels further along path BC. This is the path BC that is inside the optical flat. At part C of this light is reflected by the bottom of the optical flat and goes along CDE. This portion CDE is the reflected one, and the remaining parts goes along CF. This is the part that is not reflected, and it will be reflected at point F by the surface under the test. So some portion is reflected at the point F. This surface is the top portion of the workpiece and goes further along FGHJ, that is path FGHJ. Okay, so we are having two rays. Initially we are having only one ray, that is AB, but at the end we are having two rays. First one is CDE and the second one is FGHJ. The two beams DE and HJ differ in the phase. DE and HJ differ in the phase because of extra distance CFG traveled by HJ. This extra distance CFG is traveled by this ray HJ. The path traveled by both the reflected rays differ by an amount CFG. In other words, the second components of the rays lag behind the first by an amount equal to twice the air gap. Okay, so at all the points where the air gap is present, due to the difference in the path traveled by the rays, there will be a darkness observed at lambda by 2 distance as shown in the figure. So we can say that due to the air gap present at point F, we can observe here the darkness, or you can say a dark strip at lambda by 2 distance. As we move along the wedge to the right side, in this direction to the right side, to point K and L, after point F, point K and L, the value of H goes on increasing, and hence the phase difference between two rays will go on increasing from lambda by 2 and will reach lambda at some point. So here it is lambda by 2 at this point. Again lambda by 2 will be added and the total distance is lambda. Again if we add lambda by 2 distance, then the total distance will be 3 lambda by 2. So at every lambda by 2 distance there will be a dark strip due to the air gap present between the optical flat and the workpiece. Now let us see how we can measure flatness by the optical flat. Okay, this is the figure. An optical flat is placed on the metal surface. This is the optical flat and it is placed on the metal surface that should be tested, and it is viewed using a monochromatic light source as shown in the figure. This is the monochromatic light source. S is monochromatic light source. Optical flat will not form an intimate contact but will be at angle theta, making an inclined plane. So here it is at the angle theta. If S is monochromatic light source, at C ray is reflected in the direction CDE. S is the monochromatic light source and at point C the ray is reflected in CDE direction. Two reflected components are combined by I. This I is combining two reflected rays. First one is AB and second one is CDE. If the path lengths differ by the odd number lambda by 2, then the interference is said to have occurred. If surface is perfectly flat, then the surface will be crossed by the pattern of alternate light and dark band, which will be straight and dark. Dark line is seen passing at the point C, something like that. Okay, if the path difference FHI, this is the FHI, be 3 lambda by 2 or the next odd number of half wavelengths, then the interference will occur and a similar fringe will be seen. The next, when the path difference is 5 lambda by 2, again there will be another dark fringe. So first dark fringe will be at the distance lambda by 2, then after at the 3 lambda by 2, then after at the 5 lambda by 2. So in case of a perfectly flat surface, we will have pattern of alternate light and dark straight lines on the surface as shown in the figure A. Figure A is showing the perfectly flat surface. Now any deviation from this pattern will be measure of error in the flatness of the surface being inspected. In figure B we can see that the surface is not flat and the pattern is not having straight lines. In figure C we can say that the surface is peaked or valley, so the result is showing us the continuous circles. Let us check how we can measure parallelism by optical flat. Okay, consider this figure. Here two blocks, one whose surface is made optically flat and other whose surface is to be checked are rung on the flat surface. An optical flat is placed on the top of the both blocks as shown in the figure. Here A is the standard reference gauge and B is the gauge under the test. The L is the distance between A and B and it is measured very accurately. In case A and B are perfectly flat but the difference in height is present, then there will be equal wedge shaped air layers between the gauges A and B and the optical flat. Here the angle theta and this angle theta dash will be similar if both are perfectly parallel. In such cases, the number of fringes will be seen on the both surface will be equal. If angle theta and theta dash are equal, then the number of fringes seen at this surface and number of fringes seen at this surface will be equal. In case the surfaces are not parallel, the angle formed by the surface of two gauges with the optical flat will be different. Let the angle be theta and theta dash. If the width of the gauge block L is same for both, then the number of fringes per unit width will be different. These possibilities have been shown in the figure below. Here, if theta dash angle is less than theta, then the number of fringes at A will be greater than number of fringes at B. If theta dash is equal to theta, then both number of fringes will be equal. And if theta dash is greater than theta, then number of fringes at A will be less than number of fringes at B. Now, the next topic is interferometers. Before studying interferometers, let us check the disadvantages of optical flats. The first disadvantage is it is difficult to control the lay of the optical flat, and the second one is the fringe pattern is not viewed from directly. So to overcome both of these disadvantages, we have introduced a new instrument called interferometers. Interferometer works based on the interference principle that we have studied previously. There are two types of interferometers. The first one is flatness interferometer and the second one is length interferometer. We will study both in detail. Here the first one is NPL flatness interferometer. It was designed by the National Physical Laboratory, so the name is given NPL. Let us check the figure of the NPL. This is the figure of the NPL. It consists essentially of a mercury vapor lamp whose radiation are passed through a green filter. This is the mercury vapor light source and it is passing through the green filter, leaving a green monochromatic light whose wavelength is very close to 0.5 micrometer. So here the light which we are getting is having a wavelength of 0.5 micrometer. This light is focused onto a pinhole, giving an intense point source of monochromatic light, which is in the focal plane of collimating lens and is thus projected as a parallel beam of lights. So this is the collimating lens and this is the parallel beam of lights. This beam is directed onto the gauge to be tested via an optical flat. This one is the optical flat and this is the gauge to be tested, so that the interference fringe are formed across the face of the gauge. The fringes being viewed from directly above by means of thick glass plate semi-reflector set at 45 degree to the optical axis. This one is the glass plate that is been set at 45 degree to the optical axis. Now let us check the interference band patterns. The first one, A. The pitch and direction of the bands on the base and the gauge are same, indicating perfectly flat and parallel gauge. A is perfectly flat and parallel gauge. In figure B, though the direction of band is same, the pitch is different, indicating a taper along the longer edge of the gauge. In B, there is a taper along the longer edge of the B. In figure C, the pitch is same, but direction is different, indicating taper along the shorter edge of the gauge. In C, there is a taper in the shorter edge. In figure D, shows that the corner of the gauges are worn out. When the gauge surface is convex or concave, then the fringe pattern is shown in figure E. The next device is Peter NPL gauge interferometer. It is also known as the NPL type length interferometer because it is used for determining the actual dimension or absolute length of the gauges. Now let us check the figure of the Peter NPL gauge interferometer. Okay, this is the figure of the Peter NPL gauge interferometer. It shows the schematic arrangement. The light from the source fall on slit through condensing lens. This is the source of light and this one is condensing lens. After collimation by lens, it goes through constant deviation prism whose rotation determines the wavelength passed through reference optical flat to upper surface of the gauge block and the base plate to which it is rung. The light is reflected back in the mirror and its patterns are observed through a telescope. The fringe pattern obtained is shown in the figure in the field view. This is the field view and here we can observe the fringe pattern. Here it should be noted that the optical flat is adjustable for inclination in two planes so that pitch and direction of the interference fringe may be set to the best position. The gauge on this instrument will be absolutely flat and parallel and hence the bands on the gauge top and the base will be of the same pitch and direction but relatively displaced from each other. This displacement is recorded for each color as a fraction of pitch of the fringes and it is used for calculation of the length of the gauges. So by using this value A and B and some mathematical calculation, we can find the length of the gauge. Now the last topic is optoelectronic measurements. Optoelectronic measurement technique is a contactless method. It utilizes photodiode arrays having high resolution. Let us check the figure of optoelectronic measurement system. This is the figure. The object to be inspected is back illuminated by collimated light source. A lens assembly is incorporated to provide either magnification for dimensional inspection or reduction for the flow detection. The optical path between the light source, object and lens system is folded by using 45-degree prism in order to reduce the space requirement, and all the components are mounted on a precision slide to form an integral station for an inspection machine. Let us understand the working by an example. This figure shows a blank component in which the diameters of two holes and width of slot and position of hole with respect to radius edge of the slot have to be determined. For the sake of simplicity, it is assumed that camera viewing line has been located at the center lines of the holes. It may also be noted that the size of the important features lies within 25 mm. The measuring capability of photodiode array. The scan is started near the first feature and finished near the last feature of the object to be inspected. The latch edge information consists of a form of pulses as shown in the figure, each pulse corresponding to light to dark transition of image of the object. The start and finish of the scan corresponding to diode 0 and 1024, that is first one and the last one. And knowing the position of diode at each pulse, any dimensions can be easily calculated. So from the figure we can understand by using this diode we can measure any dimension with high accuracy. So that is the end of this chapter. Thank you.